So if you have the Abaqus file from last class, go to your temp drive, the Stent folder, double click from the folder. So it's going to set the work directory automatically for you. If you don't have the file, just go to Nexus. So that's the intermediate balloon expanded stent revision 1. So scroll all the way down. Look for the file intermediate balloon expanded stent. So download it, place it in your temp drive. So we'll finish the stent problem and you can submit it for homework. The homework is due on November 6th. So the second problem, the TOSCA topological optimization problem, it should work now. We have updated Abaqus in all of these computers, the topological optimization. So the second homework problem should work now. The homework problem is, so the homework is due on November 6th. That's the last homework. That's this Saturday. So that's the topological optimization problem. So we had to update our Abaqus installation in these computers. And now if you follow the instructions in the given handout, homework handout, you should be able to run the analysis. So Stan has updated all these computers, Abaqus with topological optimization. All right, so if you have the Stent model from last class, open it. Latecomers, if you don't have the file, log into Nexus, scroll all the way down and look for this intermediate file, balloon expanded stent. And that's the problem description. So we already assembled. We gave the material properties. Actually, it didn't need the material hyperelastic properties because we defined it as a shell surface. We gave it as a surface. It could be a rigid body because we're not focused on the balloon at all. So everyone has the file up. Okay. So as we're waiting, I'll just play that video from last class. So we want to create 3 different steps. In the first step, the balloon expands. Along with it, the stent expands. And the next step, the balloon contracts, but the stent stays with the same radius. Stent is not contracting. That's the purpose. We want to expand the artery, the closing of the artery. So we are expanding to when the balloon. So we need to define the contact between these two. So the first step is expansion. The second step, the contraction of the balloon, which the textbook was calling it as spring back, I think. And the third step is we'll apply pressure on the stent surface. It still should keep the shape intact. It shouldn't get squeezed again. It should stay with its bigger radius. So the blood pressure on the artery, the stent should not collapse back to its original shape. It should retain its shape. So that's the third step. So if you see the problem description, so we have 3 different steps. Step 1, we are expanding. Step 2 is the balloon contraction. Step 3, we're applying pressure on the stent. So that's 128 E3 Newton. So that's kilo Pascal, Newton per meter square is Pascal, right? So the blood pressure is usually what we know is through millimeters of mercury, 120 by 80 systole, diastole, that doctors usually use the millimeters of mercury when they specify the blood pressure, but that's not useful for modeling. We need to be consistent here. So that's the units. So we are using 120. Textbook is using that pressure value 128 kilopascal instead of millimeters of mercury. So that's the entire problem. We already have. If you don't have the file, go to Nexus, download it. If you were absent in the last class. So we already assembled. So if you go to assembly, you should see, and assembly, you can change the colors. Instead of assembly defaults, you can change the colors to part instances. The two parts, coaxial constraint we gave. We'll create some steps now. Assembly is done. That's all we need. So we also created a cylindrical coordinate system, the R, theta, and Z. From XYZ, we have created R, theta, Z, and the radius is in the direction of X. That's how we specified it. So instead of 1 being the X direction, now radius is going to be the 1 direction. So go to step module. So we'll create the 3 steps we just discussed. So the very first icon there, create step, create a static general, insert new step after initial, step 1, expansion, continue. So nonlinear geometry on. So we are taking this into plastic region, just a stent. So we're deforming it beyond its yield point. So nonlinear geometry. So for this, let's use the automatic stabilization, specified dissipation energy fraction. So for nonlinear geometry, convergence will be a problem. If you use this automatic stabilization, it will, whenever you have contact and nonlinear geometry, it's better to specify this automatic stabilization. Otherwise, the convergence problem will come, and we'll discuss this later on. So as of now, for every step, we're going to choose this nonlinear geometry on, automatic stabilization, choose the drop, go to the drop down and specify dissipated, and leave this as default. Go to the incrementation tab. The initial increment of 1 is going to be not enough. You need to go slightly smaller than that, maybe 0.1. I think textbook was saying 0.1, or let's go 0.05. The minimum of 1e minus 6. So initially it will attempt with 0.05. If it converges well, it takes bigger and bigger increment of time until all the 1 seconds. If it's not converging well, it will keep reducing the time increment until 1e minus 6, and it's going to throw us error if it can't do it even with this time increment. So that's what we have entered here. So say okay. So we created 1 step. So if you go to step manager, so step 1, expand, nonlinear geometry on. 1 second we are running it. Let's create 1 more step. Static general, insert new step after step 1. Give the name as step 2, spring back. I think the textbook was calling it a spring or balloon contraction. We'll leave it as spring back. Step 2, spring back. Continue. Nonlinear geometry on. Automatic stabilization. Specify dissipated energy fraction. So we'll be doing the same thing when we discuss the fracture mechanics. Next exercise is fracture mechanics of wind turbine. So we'll be doing the same thing, the nonlinear geometry and the stabilization. That's for convergence. Yes, Alex. All right, incrementation. Let's do the same thing. 0.05, the initial increment size, 1e minus 6 is the smallest increment, and say okay. So you should see step 2 underneath step 1. Otherwise, it's going to do in this order, it's going to execute the steps now. So make sure step 2 is after step 1. If not, you edit it. And if you edit it, you can't change this. So maybe delete and create again. So when you create, this is where you're choosing where the next step goes. Insert new step after this step, right? After the step 2, it is step 3. It's a pressure step. We'll apply the blood pressure on the stent. Continue. So time period 1 second, automatic stabilization, the default stabilization. Incrementation, the same way 0.05, 1e minus 6. Say okay. So you should have the initial step and the 3 steps. So we did the same thing in all the 3 steps. So we'll do one more thing in the step module itself. So this is what the textbook is suggesting you to do. We'll do the same for fracture mechanics problem also. So go to other. So this is for advanced users. So go to other, general solution controls, edit. Edit step 1. You can't edit initial. All the other 3 will change the convergence criteria. We'll have convergence problems now. So we'll ask it to run instead of, I think the default. So if you go to other general solution controls, edit and choose the first one, step 1. And the warning, it says it's for advanced users. We understand that. Continue. So go to specify. So choose specify from this from the 3 options you have. Go to time incrementation. So the default is 4 and 8. I0 is 4 and IR is 8. I'll explain it when we run the analysis. You will see the time increment it has taken, how many times it tried that increment. If at all it was not converging well, it will try this 4 times. After that, it will say it can't, it's not converging at all. It will throw us the error. So for contact related problems, we usually come and say discontinuous analysis, and this changes to 8 and 10. So if at all previous severe discontinuities were there, they will not propagate on to the next increments and next steps. So that's the discontinuous analysis. The previous severe discontinuities will not keep propagating along, and it starts this 8 times it tries are going to be the new 8 times. It's not cumulative. And when we run the analysis, I will point out where you would see this. So let's do this for all the 3 things, all the 3 steps. Step 1, expand, specify, time incrementation, discontinuous analysis. That's how many times it's going to try that exact incrementation if it's not converging well. So say okay. So again, go to other, general solution controls, edit, this time step 2. So do it for all the steps. The advanced, this for advanced users, say continue. Choose the specify option. Go to time incrementation tab, discontinuous analysis, and it changes to 8 and 10. And I think fracture problem, we probably will increase this to 10 and 20. It won't converge even by 8 and 10. We would have to increase this. So we'll see for the next problem. Say okay. So do that again for the other general solution controls, edit. Step 3, pressure. Continue. Select specify. and check mark the discontinuous analysis. So the same thing I've repeated for all the 3 steps. It won't work on the initial step. Only when there is time incrementation, only for that you can change the number of times it tries that iteration. Everyone's able to do that? All right, so go to, let's define, instead of straight away going to the interaction, let's create some surfaces. We're going to define contact between the balloon and the stent. So let's define the surfaces. So let's create surfaces from the parts, right? Because I can't, it's difficult to select the inner surface of the stent because of the assembly. So if I go to parts, I can easily create. Yes.
I just realized mine's still blue. I don't know if that is this.
So change the colors to, instead of assembly defaults, change this to part instances or materials. It will change to various different colors. So let's go to part module. Let's create surfaces here. It will propagate to assembly. So go to tools, surface. So if you are on balloon, so go to balloon drop down, tools, surface, create. So this is surf external, surf stent external. Continue and select the cylindrical surface. When you say done, it's going to ask you, do you want to select the brown color or purple color? Choose the brown color. The outside surface is brown. So if you have the options here, brown, purple, or both sides, select the brown color. So let's do the same for the stent. Go to the drop down. In the part module, go to the drop down for stent. Let's create the surface, tools, surface, create. So this is surf stent internal. Continue and select the inner surface, and it is actually created using 2 different portions. So when you click somewhere, it's selecting only the first half of the stent. So hold on to the shift key and select the other portion also. So the entire inner surface you are selecting. So you would have to hold on to the shift key and click at 2 different internal surfaces. Everyone's able to do that? Say done. So the reason for doing this is we'll go to interaction step. The next step is interaction step. I want to define contact. So when the balloon is expanding, the stent also should expand. So part interaction. What happens if I don't define the interaction? When the balloon expands, what happens to the stent if I don't define the contact? Yeah, it stays same size. It won't change. It will just pass through the stent. The balloon just expands and passes through the stent without realizing that there is a stent there. So that's how we simulate it through contact properties. So go to interaction module. The very first one is create interaction. So we have done 2 problems already on interaction. Right, we have done an extrusion problem. We have done a heat transfer also where we used extrusion. So the interaction, create it in initial step. So go to the drop down and choose the initial step. Surface to surface contact, continue. And when it's asking for us to choose the surfaces, we could pick from the viewport now, or we already created the list surfaces we already created. So go to the surfaces tab. So select the highlight selections in viewport, have this checked. So choose the balloon. Oh, I gave the wrong name here. Balloon and the stent I have here. So that should be, I will rename the things. given a wrong name there. So I'll come back to this. So the surfaces I created were in the part, right? So I'll go to the balloon surfaces, right click, rename. So the name should have been surf balloon for this. So if you have given the right name, you don't have to, but this is where it's located because I created under the parts, uncollapse the parts balloon, and under the surfaces, that's where that surface is. All right, so go to interaction, create interaction. So interaction, initial step, surface to surface contact, continue, choose surfaces. So that should be balloon, external surface. I previously gave a wrong name there. And it should highlight the surface you have created, continue. And the slave type, it's asking for the, choose the slave type, again choose surface. And this time choose the stent internal. It's highlighted in purple. Continue. Sliding formulation, small sliding. Anyone remembers the difference between finite sliding and small sliding? We have used both. For our extrusion problem, we use finite sliding. For heat transfer problem, we use small sliding. Anyone remembers what was the difference? All right, finite sliding is if you are expecting relative motion between the parts. The extrusion problem we did, the rigid dies, they were stationary, the billet was flowing, so we are expecting the relative motion. In that case, we choose finite sliding. Heat transfer problem, we chose small sliding because the pressure vessel was sitting on the concrete legs. There were two legs on which the cylindrical pressure vessel was sitting. We were not expecting any relative motion between the legs. Both are stationary. The leg and the pressure vessel both are stationary. But it's still called small sliding because of thermal expansion, it might move, right? It's not completely stationary. If you're not completely restraining it, because of physics of the problem, if it is going to slide, that's called small sliding. But the physics of the problem itself involves relative motion. You would have to choose finite sliding. So in this case, we're choosing small sliding because when the balloon expands, we want there's no relative motion. The stent also should expand radially. So a small sliding. And we need to give the interaction, contact interaction property where we say frictionless and things like that, right? So contact interaction property, it's empty now. So let's click on the icon beside it, create interaction property. Contact, continue. Give mechanical, tangential behavior and frictionless. Let's leave it as frictionless. You could also define mechanical normal behavior, hard contact. I think the book was not saying this. Big book was the instruction, homework instruction was just to define the tangential behavior. If you want to delete something, that's the icon. If you accidentally added something, you want to delete something. For heat transfer problem, we went to thermal and we chose thermal conductance. We don't need that here. So just tangential behavior, frictionless. And if you have difficulty, this window is too big, so you can't click OK. So close it. It will ask you to save. So save changes, yes. And that's the interaction property of frictionless. You're saying frictionless here, and you're saying small sliding allowed based on physics. And those are the two surfaces, balloon surface, external, and the slave surface, stent internal. And we created this in initial step. And we will allow it. If you go to interaction property manager, we created this in initial. It will keep propagating throughout. Everyone's able to do that? Or let's keep saving it. It might crash because it's a nonlinear geometry problem. All right, let's go to load module. So our entire problem is depending on this load module. So create boundary condition. There's a second icon. Let's choose initial step. Let's choose displacement or rotation. Continue. I want to select the entire assembly. I don't have that option here. I have balloon and stent. So close this sets. So if you close it, you can select in viewport. So we're going to draw a box around everything. So if you say select in viewport, draw a box around everything. And before you say done, give the name as set entire assembly. Set entire assembly. And you have already chosen it. You have drawn a box around everything. And then say done. So this is where this is an important step. We're going to constrain all of these degrees of freedom. We'll leave only U1 unchecked, but the one now corresponds to the X direction. In X direction, it's allowing because the coordinate system here is global. And in initial, all of these are zeros. You can't give non-zero boundary condition in the initial step. You could do that in step 1, step 2, and so on. If at all you need to give non-zero boundary condition in initial, what is the way to do in Abaqus? If you want to give non-zero magnitude, what is the procedure? So instead of defining it as a boundary condition, define it as a predefined field. That's the third option. We have done that for heat transfer when we had to give temperature as 20 degrees centigrade. It was non-zero at initial step. So that's the predefined field. Here it is fine. The initial boundary condition. Fix all of them. Leave out only U1, but change the coordinate system. Instead of a global coordinate system, pick the arrow here and go to the datum coordinate system list. We already created a, so when you select the cylindrical coordinate system, it's highlighted in green. That's the radius. Radius direction is in the direction of X. That's the global X. So global X is degree of freedom 1. Degree of freedom 2 is Y. Degree of freedom 3 is Z. Rotation about X is 4. Rotation about Y is 5. And rotation about Z is 6. Temperature degree of freedom is 11. So that's Abaqus universal notation. So now radius is along the global X direction, meaning radius is getting the degree of freedom 1 now. So choose the cylindrical coordinate system, say OK. The U1 that you are allowing now is the radial direction. Uniformly, it's going to expand in contract in the radial direction. All the others, your initial step itself, you are constraining all of this. And when you say OK, so go to the boundary condition manager. You created this boundary condition. You are allowing only, you left out only the radial direction. All the other directions you constrained. Initially it was 0. You let it propagate throughout. So throughout all the other boundary conditions, all the other steps, they're going to be 0. The 2, 3, all the other degrees of freedom. Only radial is allowed. Yes, Hayden.
I don't have all the blue and orange arrow stuff on. I don't either.
So maybe you didn't select the region, set entire assembly. So see whether it's pointing to any region there, or edit region and draw a box around everything. So let me see. Fine. to make sure your coordinate system is as I have R, T, and Z. So, on to the all this. So it's in the Z direction now. That's the- this is the program. Yeah, the coordinates. Yeah, I use 0.5 or Z is equal to 0, so other way X and Y equal to 0. So the coordinate system, if it's not done properly, it's not showing those arrows.
Yeah.
Okay. Okay, so if your coordinate system doesn't look like mine, so what I want you to do is, so I'll show that again how I created the. So the R, T, and Z, if it doesn't look like this, what I want you to do is go to assembly in your tree, uncollapse the features, cylindrical coordinate system, right click on it and set delete. Yes. Let's create the coordinate system again.
I just got it. I don't know why. I believe it.
It has probably gone to the global coordinate system, which is not accurate. Let's go to tools. Once you delete it from the tree, assembly features, find that coordinate system cylindrical and delete it. The way we created it is go to tools, datum, coordinate system. CSYS is the new coordinate system. 3 points. Give a proper name so that you can easily identify cylindrical CSYS and choose it as cylindrical coordinate system. Continue. Select a point to be the origin where it wants to put the center of that RPZ axis. As of now, it's putting it there. I'll go and choose the reference point here. So that's the center of. So I'm going to delete this. So choose the reference point there. So from the center of this balloon, it expands radially. That's why I'm choosing that reference point there. Then it's asking select a point to be in the R axis. So choose the point on the circumference of the tube. There is a point there, or you could enter 1, 0, 0. It doesn't actually have to be part of this geometry. Any point in the, if you want the radius axis to be in the X direction, so you could enter 1, 0, 0 also. And it's asking select a point to be on the R theta plane. So enter 1, 1, 0. So that's going to be, the Z is going to be 0. So it's on this plane. Z is 0 there. So that's why Z, any X and Y you could give 1, 1, 0 and enter. And that's going to put the RTZ there and cancel. It's going to keep creating the datum coordinate system. So cancel out of this and close it. So you should see the R, T, and the Z axis clearly. If they're squished, probably you didn't pick the directions properly. Once you have done that, go to this boundary condition manager. The boundary condition one, edit. So the coordinate system is gone because we deleted it. So choose the CSYS, the arrow beside it, and go to the datum coordinate system list from the bottom and choose the cylindrical coordinate system and say OK. And that's the, so the region is there. Initial step, the cylindrical coordinate system. I'm allowing only the radial direction displacement, which is the one direction. And when you say OK, You should see all those arrows. Everyone's able to do that? All right, let's proceed. Let's create another boundary condition. So this boundary condition is for expansion. That's the first step, right? The balloon expanding. We'll create it in step 1. So go and create. Click create. BC2. Instead of initial step, I'm creating this in expand step. Mechanical, displacement or rotation. Continue. Select the regions for the boundary condition. I actually can pick the go to sets. So go to sets. We already have a balloon, entire balloon set. So the entire balloon is expanding, or you can pick it from the viewport also. The reason why we give names is when you look at the input file, which is a text file, you can understand just looking at the text what you have done. So sets, pick the set entire balloon, continue. The global coordinate system, datum CSYS list, pick the cylindrical coordinate system. Select all the displacements and rotations, leave them as zeros. We're not changing them at all. Only the U1, you can make this as, I think the textbook was saying 0.3028. Let me see it's there in the problem description. So the first boundary condition I created was initial, everything was 0 except U1. The second boundary condition for the entire balloon region in the expand step, everything is 0 except U1 is some positive value. So 0.3028, and the coordinate system I'm using is cylindrical. So by that, what I mean is this U1 is the radial direction. So radially, I'm expanding it uniformly, the balloon. So 0.3028 and say OK. So it's created in step 1, but it is propagating to step 2 and propagating to step 3. I can actually inactivate it. So go to step 2, boundary condition 2, step 2, and you can say deactivate. Otherwise, it will try to expand it in every step. Only in the expansion step, when the balloon is expanding, we should take that radial value of 0.00028. In all the other steps, it shouldn't expand. Everyone's able to do that? So this should give you a summary of all the things you're doing, the boundary condition manager. So let's create one more boundary condition. So the next boundary condition is again for the entire balloon region in the step 2, which is spring back step. Everything is 0 except U1 is negative value. Let's do that. So create boundary condition, choose step 2, spring back step. So the balloon will contract now. Displacement rotation, continue. If the set is already open, choose the entire balloon, or you select it from, you will see sets here, click on it. If that doesn't automatically open to you, click on sets and then choose the entire balloon, continue. The coordinate system. So click on the edit button and change the datum coordinate system to cylindrical coordinate system. Fix all of these things. U1 to all the way to U rotation 3. U1 is a negative value now, minus 0.00012, minus 0.00012. So radially, the entire balloon is shrinking. Say OK. So the cylindrical coordinate system, we created this in step 2. Only U1 is negative value. Radially, uniformly, the balloon is going to contract. And say OK. It's created in step 2, but it's propagating to step 3 also. We don't want the balloon to keep contracting, right? So let's click on this propagated and say deactivate. So only in step 2, the contraction, radial contraction needs to happen. Everyone's able to do that? It's a repetition of the same steps. And finally, we have a loading condition, a pressure loading, external surface of the stent. So if you have the problem description open, you will understand what we are doing. So the external surface of the stent region, in the step 3, we're going to apply a pressure of 128 kilopascal. So that's the pressure applied by the arteries on the stent. So that's the 128 kilopascal. So pressure is a loading. It's not a boundary condition. You can do the displacements here, temperatures, displacements. Those are primary variables which are part of the differential equation. You can do them through boundary condition. Pressure, forces, those are, and fluxes, those are loads. So you would have to go and create a load. This is in step 3, in the pressure step. So choose pressure instead of concentrated force. Pressure, continue. We already, we didn't create the external surface of the stent. So it's fine. So if the set opens, you can close it. We'll select from the viewport. So close this entire thing. We'll pick from the viewport. So select, click on the white. External surface should be easy to pick. If it's internal surface, it would be a headache. So click on the spirally stent, and I think it's made of 2 different parts. So rotate it, hold on to the shift key and select the other half of the stent also. Yes, Frank. Which region?
Yeah.
That's what I'm doing instead of, so I'll do that again. So we don't have a surface created for the external stent. So we are picking from the viewport. We don't have a set already. So I closed, so it was suggesting me to pick from this list. We don't have a list for external surface, so I closed this. And I came here and I'm picking from the viewport. I clicked on the spirally stent, and I didn't pick the entire external surface, the other half. Hold on to the shift key and select the other half of the stent also. So then the entire external surface gets selected, and you can give a name now, surf, stent, external. We didn't need external surface until now. Pressure we need to apply on the surface. So done. And give a magnitude of 128 E3 kilo Pascal is Newton per meter square. And there is no coordinate system here. Pressure is always normal to the surface you pick. So there's no coordinate system here. Yes, Frank? So I'll do that again. So cancel whatever you're doing. So create load. So choose the step 3 pressure. Choose pressure. Don't choose concentrated force. We're selecting we're applying pressure. Continue. So if at all the surfaces list has popped up, close this. So from the viewport, zoom in and select the one half of the stent and rotate. Hold on to the shift key and select the other half of the stent. So make sure you are selecting only the stent surface. So give a proper name and save it. Say done. And give a magnitude of 128 E3. Now do you see this menu? So there's no coordinate system. Pressure is always normal to the surface you selected. and say okay. And you should see arrows going into the surface. All right, so save it so far. So that's all, that's the entire problem. We just need to mesh and run the analysis. Everyone's good so far? Yes.
The problem with the boundary condition, maybe for not.
Yes. Sure. Okay, you created this in initial. Right? You couldn't do, you can't enter any non-zero in initial, so move to the right. So now you have values here. Deactivate here. And this. Okay, this should be it here. So move to the right. Is the yeah, here you chosen step to spring back, which is compression. So you need to use a compression displacement. Yeah, that looks good. Distance and the loading you have already done. Yep. So this load needs to be in the step 3. Pressure, we are applying pressure only in the very last step. After the balloon contracts, we're applying the pressure. So if at all you applied the load in some other module, so go to load manager. So it's created only in the very last step, the pressure step. So that's when all the plastic deformation already happened for the stent. So it's permanently deformed. It can't go back to its squished state. So it will try to retain that shape. And that's when you are applying pressure. So go to mesh module. So mesh by part. So choose, if you're an assembly, go to part. You would get a warning, right? If you in assembly, if you brought it as a dependent part, dependent mesh on part, that's how you fix that problem. You mesh by part. Then if you brought it in assembly as an independent, then you can mesh as an assembly here. So first I'm meshing the balloon. So go to the drop down, choose balloon. Seed part, we'll do we already done meshing already, so we'll quickly complete meshing. So seed part, for other exercises, we concentrate on the meshing. So seed global part, 0.0001. That's what the book was saying, 0.0001, say okay. And that's decent enough, done. Element shape, assign mesh controls. That's where you assign the element shape. Assign mesh controls. I will leave this as quad dominated. If at all it can't form quadrilateral, it's a cylindrical surface. If it can't form quadrilateral elements, it will pick some triangular elements at that location. But quadrilateral is dominant. That's the quad dominated. If you want only quadrilateral, you can pick only quad. I'll leave it as quad dominated. Say okay. Element type, which is the S4R. S4R symbol that you see is the element type. Choose the geometry, the balloon, done. Here, choose the surface element type. Go to the drop down, choose it as a surface. So that's the SF surface element, M3D4, and reduced integration. So we will learn what reduced integration is at the very last class. We'll learn about Gaussian quadrature and reduced integration. It saves us time. So your element type is surface SF M3D 4 node reduced integration. So 4-node quadrilateral surface element, say okay. And then mesh the part. This is the last step. So mesh part is a very second icon there in the panel. Mesh part, yes. So it was able to do the quadrilaterals. And if you want to check the aspect ratio, anyone remembers the quality of the mesh? It's mandatory to report your mesh quality. Otherwise, no one will trust your results if you don't specify the aspect ratio and things like that. Anyone remembers? How do you check? Yes, Priyanka. Yeah, go to the top mesh, verify, and select the part and say done. So go to the shape matrix tab, aspect ratio greater than 10, highlight that and say highlight. Aspect ratio is actually 1, exactly 1. So that's the best you can get. Anyone knows what's aspect ratio? Anyone remembers what is aspect ratio? So aspect ratio is so maximum length by minimum length of that element. Say you have so many quadrilaterals. So let me draw it as a. So that's the max length. And this is minimum length, and you have so many quadrilaterals there. For each of them, max by min, it was exactly 1. So that's the best kind of meshing you can expect. It won't happen for stent. Stent has complex geometry. Hope we get somewhere around 3. Less than 3 is good enough for us. Otherwise, you have some weird. So if you have something like this, in this direction, say whatever this direction is in Y, say this is in X. In X direction, your field is changed. Say temperature problem I'm solving. In X direction, I have temperature varying drastically, but in Y direction, the temperature is not varying at all because this element edge itself is very small. It won't give a good results. You can't trust the results if your aspect ratio is say greater than 3. So you want proper proportions of your each element. Does it okay? The mesh. So for your presentation, I am expecting to see the mesh quality. You would report the average aspect ratio. It's okay if it is less than 3. So go to the next part instead of balloon now. So keep saving it. It might crash. My Abaqus is stuck. So keep saving it. So stent, choose the stent. Global seed part, the same 0.0001. 0.0001. Done. Assign mesh controls. So I'll show you the problem we get and then we'll come and fix it. I will leave this as hex. It won't be able to fit a hexahedral element for this complex shape. We would have to come and change that to tetrahedral element. But just to show you that warning message or error message, I'm going to leave this as hex for now. I'll come back and change this. So assign element type S4R. So we need to assign element type, select the geometry, done. We need to say that it's a 3D stress or heat transfer or a plane stress, whatever that problem is. So this is a 3D stress problem. So that's what element type means. Element shape means whether you're using quadrilateral or hexahedral or tetrahedral is 3D triangle. So 3D stress, linear. So C3. So C3D8R, that's the, okay, D8 because it's a hexahedral. Hexahedral is similar to our cube but unequal edges. So hexahedral is not hexagon. It's a hexagon is a 2D geometry, right? Hexahedral is something like this. So you have hexahedral should have 8 nodes. So that's a hexahedral element. It's not exactly a cube. So you have 8. So that's a hexahedral element. 8 nodes similar to cube, but lengths are not exactly equal. The surfaces are not exactly perpendicular. That's a hexahedral element. So 8 nodes you should expect. And that's the problem. It can't use the hexahedral element for this geometry. We'll get an error and we'll come and fix it. Say okay. And then mesh part. And when you say that, it gives you an error saying selected regions cannot be meshed using the assigned element shape, which is hexahedral. It's a very complex shape for the stent. So you can't use the assigned element shape. It itself is suggesting you the solution. Use the tetrahedral shape. If you have complex geometry, use the tet shape. That's going to solve your problem. That's what it is saying. So read the warnings or errors it gives you. That itself is suggesting you the solution. So the way to fix it is go to the assign mesh controls again. So instead of hexahedral, choose tet, which is tetrahedral. Tetrahedral looks like it's a 3D triangle. So that's a tetrahedral. So tetrahedral will have 4, I think, 1, 2, 3, only 4 nodes. So tetrahedral, okay, and the color changes. And go to the assign element type again, which is S4R, and pick the stent, done. So instead of quadratic, change it to linear. And you have the C3D4, the tetrahedral will have only 4 nodes. Previously, the hexahedral had 10 nodes. So this one has only 4 nodes. And yeah, let's leave it as it is. C3D4. That's the element type I want. 3D stress. A tetrahedral element. That's the element type C3D4. If you want to know the degrees of freedom for that, just Google for C3D4 Abaqus element. It will give you the translation, rotation, all the degrees of freedom it has. Now, if you try to mesh the part, which is the second icon there, now it should allow you without giving you the error message previously you were getting. So that's the 3D tetrahedral element it used for that complex shape. I'm not planning to do mesh verify. It's going to be bad. Let's see, mesh verify. And select this entire geometry, done. Highlight. So the average aspect ratio is 1.85, which is really good. Anything below 3 is okay. Anything close to 2 is fine. I have 1.85 is really good. The highlighted regions, wherever the spirally section is joining the other spirally section, I think that's highlighted in yellow. The yellow color has significance. So if you go to the last tab, analysis checks, the yellow color is for warnings. Say the convergence problems you will get during the analysis. You want to fix all of those, but yeah, this is just a practice problem, right? So you can refine the mesh or you can make the mesh coarser. The aspect ratio has to be as close to 1. The average aspect ratio, get it as close to 1 as possible. If you have it in purple, you will definitely have errors when you run it. So you have to fix it. Yellow is fine. It won't cause any problems. It might take time to converge. So save. So that's the meshing. The last thing is job. We create a job and run the analysis. So save it. So far it might crash. So save. Go to job manager, create, give the name job stent 2021. So make sure before you submit this job, so make sure your working directory is, so file, set work directory. So that's the folder in C drive. Some of you are working in downloads folder. It's really difficult to know where it goes. If you run it from the downloads folder or from your pen drive, create a folder in the temp drive and work from there. Yes. File, set work directory. So if at all you download from Nexus, maybe you copy it to the temp drive and double click from there. I'll come, Alex, one second. So when you run it, it's going to be a headache. So you are working in downloads folder. They are there. Double click here. It's automatically going to take your work directory. If you double click on the folder, so you see no file that one there. You should point to that folder. Job scan. If it gives errors, will come and fix it. Do you have any problems?
No.
Tools, you can run it and see what's the problems. So you can submit it. So it should go to your camera. To make sure it's going to the camera, it should be otherwise the part. So you should see a log file now. The log file means it's running now. If it disappears, it has finished running. So submit the analysis, make sure you copied it to your temp drive and you double click from there. It sets the work directory for you already, file set work directory, or create a folder and save it there and then run it. So if you submit it, it will take at least 5 minutes, I think. You will have initially, it will go through some convergence problems. That's to be expected, nonlinear geometry. If at all there is no, if we missed anything, the coordinate system, if you use global and radial, it would give us errors, no? Saying you have mixed coordinate system you use. If it passes the input file check, let's see. If it passes the input file check, go to monitor, don't go to results right now. Just go to monitor. So it has gone through the input file processor successfully. So I didn't miss anything. There are no serious errors, but during the analysis, I might get convergence errors. It will take some time. Don't open the results right away. Don't wait for it to say completed and then only go to results. But you can always monitor when it is running. Go to the monitor. There's a lot of information there. It hasn't started running. So it's taking time. Okay, so the first increment. So 7 discontinuities, severe discontinuities with 0.05, 0.05, and the next time it tried 3 discontinuities. So it reduced it. It tried 0.05, then it went 0.05 3 times it tried. So now it increased it, it was converging well. It went slightly higher time increment, and it will keep doing it. All of this is still in step 1. Step number is here. That's the increment, the severe discontinuities. That's what we try to play with it. The 8 and 10 we give. The number of times it's going to try. If at all it can't do it by this 8 and 10, we will increase this to 20. If you define your problem well, your mesh is really good. You should see this time increment. Now it is taking bigger and bigger time increments. Means it's a indication that now it is converging well. So the first step is all the way until 1 second, right? Right now it's only at 0.28 seconds. So now it is increasing the time increment well. It's converging really well. So that monitor gives you the how well the problem you have set it up. Any questions? I saw hand.
Yeah, my understanding is that independent variables aren't arranged in specific order.
Or 34. Point zero. No, it's zero. The next one is 0.1. It should be less than that's actually what it was. Then it is 0.1, then it should be 1. Yeah, the errors that give you, so what I suppose, I went to this monitor, I went to this data file, I needed more information. So I went here, 2.58 I gave away. Field status.
Thank you.
So that's what you use monitor for troubleshooting. So submit it again. Now it should work. Let's wait for it to get the process check, input file process completed. So there's no serious errors. Warnings are fine. You will expect to get warnings here. So now wait for it to take a figure and figure. Initially it will struggle, severe distant images.
Okay, thank you very much.
So now mine is in step 2 and it is taking smaller and smaller increments. And we will see if it can't, it will say error. It will ask me to try smaller increment.
If it takes forever, it's used by the trash.
No, it's coming. So let's wait and see.
Is yours?
Anyone had any errors? Mine is in step 2. So now it is taking slightly bigger increments, step 2, so 0.0026 and so on. So it should go all the way to the total time 2 seconds, right? That's when the step 2 completes. Anyone had any errors? So if you get errors, these are your best debugging tools, the data file, search for error in data file, search for error in message file. So go to this data file and you can type text to find error. If at all there was error, it would point to that location and it will give you some indication where you could have gone wrong. If at all it was pointing to any errors. If you don't have any errors, just wait for it to complete. So it's taking bigger increments now, but it's slow. You have errors? Yep. Yes, let's see. Errors are good, so you will see what the problem is. Missing property definition, so you didn't use the material property. So let's see the solution there. I could find the solution for property. Only thing is inspection. We need to assign. Yes, you need to assign a group.
So, what are the last questions that we have from the- Finally, we could not get some documents.
There are no obvious errors, but during the so once it says, yeah, input file process completed. Now we can go to now. It will take some time.
Yes, and if this node, there's penetration and a contact force error. So that might take. That popped up, it was running for a little bit and then it.
There's some penetration, that's the overflow. If at all the assembly was not, there's some penetration during the assembly, so that's what I was asking you to adjust the overflow.
So that's like the, so that the stent doesn't like pierce the balloon.
Yeah, so we should.
Then you could also.
So mine says completed, all the 3 steps are complete. Anyone else had it as completed? Awesome. So anyone incomplete or still running? Is it still running or error?
No, mine's still running.
Okay, running is fine. If you have error, Alex,
Yeah, I'm going to.
okay, running is good. You have error?
It's running.
So just be patient. So the ones who have completed, who got the message as completed, dismiss this monitor, go to results, play the animation and save the animation. If you have difficulty, I'm going to repeat it anyways, but I want to see whether you can save the animation by yourself. So Miser's stress is fine. Make sure that Miser's contour, save the animation. We have done the animation 2 times for heat transfer and the dynamic, the This is the other one, extrusion problem. So repeat those steps. So I want you to submit this CAE and ODB file on Nexus. The video is fine. I didn't ask in the homework, but you can submit the video also on Nexus. The second problem should be pretty straightforward. The instructions are really good. The topological optimization problem. Now, when you run it, you shouldn't get any errors. All of this, I think, Theo, if you're working on your laptop, Abaqus, if you have, you probably need to update the Abaqus to latest version. The topological optimization, it needs to be updated. Shen, if you want to update it, please see Stan. I think he's gone to a marathon now. This week he's not going to be available. Next week you can run it on the ISCC computer. So let me know, guys, when you are complete. So does the animation make sense to you? Slow down the animation. So you can see the three steps, the expansion, contraction, and the pressure step. It should still retain its shape. Nexus. This is a homework problem. Go to a contour. So Mises contour. Now you can save this as an animation. You can remove this. Yeah, just contour and save animation. And you should have this running, otherwise you will see only static image. It's pretty good. And it's holding the pressure step. So when it goes to step 3, it's retaining it. So slow it down so someone can actually observe all this. In step 3, it's retaining the shape.
Should I slow it down?
Yeah, slow it down. You know how to do that?
Yeah.
But the analysis completed.
Yeah, the analysis is made and there wasn't.
So you're looking at scale.
Okay.
This is the time evolution of the problem. The scale factor, which is not relevant. We need to know this is the time evolution of the problem. It goes from increment 0. So you will see it here. Step 2, step 3, increment all the way. So slow it down to understand it. That's where we are doing the animation option. And you have to move this. Step 1, now is step 2. Step 2, this should contract. Yeah, restore it. Step 2, it should contract, but it still should stay there. Step 3 is applying the on the surface. But already plastically deformed, it should retain its shape. That's it. Anyone still running? Completed the analysis? And then contracts, balloon contracts, that's good. It should stay like that.
Yeah, but it doesn't.
It's staying.
Just.
Balloon, you will remove it. So I'll show you, I'll explain the problem.
But then people have to see.
So it comes to so remove this is complete. Step 1 is expansion, both expanded. Step 2 is spring back. So only this contract. If this has already plastically so many deformation happen, it stays put like that. It can't go back to the original shape. Step 3, you're applying pressure, but I think it will extend you to stop it. Right? So there are some step definition, more with conditions. So you have this propagation. So it's keeping on the step 2, created the extension, and then you that's fine. So running but you understood the problem. Right?
Yeah.
Somebody
I mean, around the mesh, right?
Yeah, only the running. Okay, so if you get an error, place it in a zip folder. It will reduce the size drastically. So right click on that ODB file and say send to compressed zip folder. All right, so I'm going to create the animation. If at all you had any difficulty, go to results, the contour options, Miser stress. I'll change the font size. This may be a little too big. And I don't want the bounding box. That's the bounding box. So if at all your part is overlapping the text portion, move it away. So that's the pan option to move this. And have the animation running. It's too fast. So I'll go to the animation options and slow it down. So in expansion step, both the balloon and the stent are expanding, which is what we wanted. And in spring back step, this is contracting, but it can't pull the stent back because stent is already plastically deformed. I'll show you the plastic deformation in a second using the peak value, the plastic equivalent strength. So in spring back, only the balloon contracts, this stays put. And in pressure step, we applied 128 kilopascal. The artery is putting pressure on the stent, but the stent needs to hold its shape. Otherwise, there's no purpose of putting the stent there. So once this makes sense, so make sure I saw few of you use some other animation. Make sure you're using this animate time scale, animate time history. That's the time evolution of the problem. You have others. Most of the time we don't use this. So just the animate time history is the one you want. Make sure this is running. Go to animate, save as. Give a proper name. So stent animation. What's the other important thing that we always miss? So leave this as AVI. Anyone remembers? Yes, go to options, change the compression codec from Microsoft RLE to video 1 and say OK. So the two mistakes are the video is not running here and the compression codec, you pick something wrong. So wait for it to say the stent animation.avi is saved and it will put it in the same folder you are running, the work directory. So date modified. That's the stent animation. Right click, open with Windows Media Player. And that should make sure this is running in finals. If I see a static image, you lose points. So make sure your video works when you open with Windows Media Player. Is it okay so far? You have
It's still running.
Oh, that's fine. Let it run. It's okay. We are also interested in the plastic stent. Misers. The problem with misers is, again, misers is a scalar. It's not a vector or a tensor. It's a equivalent in 1, 2, 3 directions, right? X, Y, Z direction. Equivalent is one miser stress. It's good, but you need to compare it with the yield stress of the material. That's why we have another measure called peak. So if you go to the drop down here and select the peak, plastic equivalent strain, PEEQ, and this is again a scalar like one miser, but this is a strain, not the stress. If it is greater than 0, definitely plastic deformation is happening there. If it is 0 means blue color here. If it is in blue, it has not plastically deformed. You can see it's very uniformly plastically deformed, which is what we wanted. We don't want a strain accumulation in few regions. If you have one region more strain than the other regions, that region might chip off. We don't want that. Uniformly, we want the strain, and that's what you can see the similar colors here throughout. So most of them are around 5.5 peak value.
Is this, these values, are these based off of that, Poisson's ratio and whatever number we put?
No, this is equivalent strain. XY is equivalent strain. So if anything greater than, so this is a good measure. You don't have to compare with another thing. So if it's greater than 0, it can't be negative. It's equivalent. So if it is 0, means it has not yielded at that location. Anything above 0 means at that all the locations it has plastically yielded, and it's retaining its shape because of the plastic deformation. That's why we are looking at peak value rate. It's retaining its shape. It's not going down. And if you want to see the, so you don't have to do this. I'm going to quickly create XY data from field output, continue, and I'm going to choose say unique nodal, the peak values, elements or nodes. And that's the advantage of creating the node sets already. So if I go to node sets, and if I choose the entire Stent and save, it takes some time, dismiss, and now go to XY plot. So those are all the Stent nodes. I can make them plot individually. So that's the time evolution. Again, my scale is messed up. My font is messed up here. I'll quickly fix the font. So you don't have to do this, and we have done this before in other examples. So I'll change the x-axis also. All right, so you can plot just one of them, or I'll hold on to the shift key and I'll plot all of them. The reason why I want to do this is I want to see whether there is any strain accumulation. It takes some time. So most of them would stay at a particular peak value. Yeah, so those are all the peak values. They're pretty staggered from 0.4 to 0.7, most of them are. So that's the uniform straining that we want to achieve after the Stent expands. We want it uniformly radially expand. Yes. Fine. That's fine. You don't have to do this. We have done this for other problems, right? So I created an XY data. So create XY data and ask it to plot the XY data. Yes. I have node sets. Go to node sets.
No, I have everything.
Oh, shift. Select the first one. Hold on the shift key. Scroll all the way down and select the last one. No, scroll all the way down. Yeah. Release the shift key. Go all the way down. Now shift and last one and say plot. Plot. No, all of them. So there are plenty of nodes. So that's why it's stuck. So I'm closing the window here. I don't need that anymore. Yes.
I got it to work. I just don't know which place to put that.
Where to submit, that's what I'm going to show now. So if at all your ODB file is too big, let's see the ODB file here. So that's 200 MB. You can't submit it on Nexus. So right click on this, send to compress zip folder, and that should reduce it by 10 times. Just the ODB file. Or you want to put the entire folder, it's up to you. The ODB file, but reduce it by half, 106 MB. Is it because of the plot I have? You can't upload anything above 100 MB, I think, in Nexus. That's a hard restriction. You can email me. It will send it as a Google Drive link instead of Nexus. If yours is more than 100 MB, you can't upload to Nexus. Just send me an email. It will upload it as a Google Drive link. Yes. Fine. Just the zip folder. Others you can upload to the Nexus, right? The CAE file upload to Nexus. The animation I was not asking, so it's up to you if you want to submit. All right. So wanted to do the wind turbine blade, the modeling of wind turbine blade. I don't think we have enough time. So that's the next exercise. We'll do it slowly. We'll create a 3 blade, but the goal here is not the 3 blades. We will actually do fracture mechanics on just one of the wind turbine blades, but I'll just show how we can create, so you will know more in the assembly process. So maybe you can just watch. I will quickly do it and we can repeat it on Monday. So I'm going to create the wind turbine blade assembly. I can do it in 10 minutes. It's okay if you can't create it, you can just watch. Anyway, we are not using the 3 blade model. We'll do it only on 1 blade. So I'm trying to model this, the 3 blades. So the plan is to use, so I'll create 1 blade and then pattern it, radial pattern. So my goal is to create 1 blade first. And the way I create the blade, you can see it's twisted. It has different cross sections. Imagine the rectangle at various locations. If you take a section cut, the rectangle has different dimensions throughout. So the way to do that is through loft option. If you have used it in SolidWorks, it's the same here also. And I'm going to quickly do that. You can just watch. We'll repeat it on. So I'm going to create a part, solid extrusion, and say 2 meters. So I'll draw a rectangle. The dimensions, I'm picking something 1 by, say 0.4, and my fonts are messed up. So 1 by 0.4, that's the rectangle. The important thing here is I want it to be symmetric about the origin, because I'm going to use loft option. So I'm going to create 2 axes, the vertical axis, vertical datum axis at 0, 0, and then a horizontal datum axis at 0, 0. So the rectangle is not exactly centered about the origin point. So I'm going to use conditions here. So constraints, I'm going to fix the horizontal one. I'm going to fix the vertical construction line. And I'm going to apply symmetry. Symmetry, the horizontal axis and these 2. So the rectangle move, right? And again, the symmetry constraint. Axis of symmetry is now the vertical axis and the vertical edges of the rectangle. So now the rectangle is perfectly defined. The center of the rectangle is origin. So I use the symmetry conditions to achieve that. The reason is I'm going to use loft so that I need some reference. The origin will serve as a reference for me. So far it's pretty simple, right? All I did was construct a rectangle of some dimensions. I'm going to, before I extrude it, I'm going to save the sketch. We brought in the sketch before, but we haven't saved a sketch. That's how you save the sketch. Save sketch as, I'll leave it as sketch 1. And when I did that, you would see it went to the sketches option here. So that's the sketch 1 I just saved. So I don't have to keep drawing the rectangles. I can use the same rectangle, which is symmetric about the origin. That's why I saved it. So if I say done now, it will ask me for extrusion depth. I'm okay with say 0.2. So I created a simple block of rectangle. So I'm going to create a datum planes. Loft, how it works is I create multiple datum planes. On that datum plane, I create some rectangles. All those rectangles needs to be joined to form a wind turbine. So that's the plan. So first I need is tools, datum, a plane, offset from plane, offset from this face, enter value, and that's the direction I want. Say okay, 2 meters, and that has gone. So that's the plane I created. We'll work on this and we'll create more planes. So I want to draw a rectangle on this, and I'll use a loft feature from this rectangular block to this rectangle sketch. So I want a rectangle feature here on this datum. So I'm going to create a planar, wire planar, and select this datum plane. Select an edge axis that will appear. I'll select this edge. And I have to create the same rectangle again. Only thing is I'll scale it down and rotate. So I already saved the sketch, so I can bring in the sketch. So add sketch. That's the previous sketch I saved. So bring it in. And it's exactly overlapped on the previous rectangle, but I can scale and rotate. That's the plan, right? The wind turbine, the cross section, as you go from the hub portion to the end of the blade, the wind turbine cross section decreases. So that's what I want to scale first. I'm going to scale about the origin point, and I'm going to scale it down by 50%. So that has become my rectangle now. So this has become 0.5 and whatever this dimension I give. And I will rotate also. You would see the blade twist, right? Any direction wind comes, the blade should be able to catch hold of the wind and rotate. So that's why I have to rotate the cross section also. Rotate about the origin point. And say I'll rotate by say -30. Minus means I'm rotating by clockwise. Plus is anti-clockwise. So the same rectangle I have drawn, I just scaled it down 50% and rotated it. And I'll show if I say done now. Done. And you would see I have drawn the rectangle, 50% of the previous rectangle. And I rotated it 30 degrees clockwise. I'm going to repeat the same process. I need at least one more section. You need as many as possible. I'm going to repeat the same thing. Tools, datum, plane, offset from this new plane, enter value, direction is okay, say 1 meter. And I want to draw the rectangle on this. Select an edge or axis that appears. I'm going to pick this edge. So it goes into the sketch mode. Again, I bring in the sketch, add sketch, sketch 1. And I'm going to scale it down now about the origin point by, previously I did it by 50%. Now let's say I'll decrease it to 25%. I'm scaling down by 1/4. So that became a very small rectangle. And I also rotate it say to 45 degrees clockwise, -45. It wanted the origin. So 0, 0, about the origin I want to rotate and -45 degrees. And that's that rectangle there. And if I say done, I can see what I've done. So I have a rectangular block. I have one rectangular cross section, another rectangular cross section. I need to do multiple locations. Say I have only these 3 locations. I'm going to loft. So shape, solid, loft. The same thing in SolidWorks also. And insert before. I'm going to choose this section, done. Then insert before, I choose this section, done. And before this, insert. And I want to select this rectangle. So I'll go to the wireframe mode. I select just this rectangle edges. not the faces. So I went to the wireframe mode just to see the edges. Say done. So make sure section 2, which is the middle one, is actually middle here. Otherwise, the loft will not work. It will go in one direction. It can't go in one direction, come back in another direction. It has to go from one end to the other end. So that's the way I picked these sections. And when I say OK, it should create the wind turbine blade. And if we go to the 3D solid, so that's the wind turbine blade. You can see it's curved. So at various, if I pick more sections, I give more, so I can control this twist. You want the blade to be twisted so that it can, air can impact on the surface at any angle and still the blade rotates. It's not a straight section. It has to be slightly twisted. That's why we rotated it. All right. We will stop here. We will do this on Monday again. And if you need this for your project, we are meeting tomorrow for projects. If you need any help, please drop by. Otherwise, mention your time, convenient time on Excel. I'm also okay to meet on weekend over Zoom. All right. We'll stop here. We'll do the fracture mechanics next week. Any questions?